Hello, I'm Hamish Johnston, editor of physicsworld.com. I'm at the Royal Society in London for the Spin on Electronics meeting. Researchers from all over the world have gathered here to explore the science behind Spintronics, an emerging technology that could revolutionize the way that electronic devices work. I'm with one of today's speakers, Professor David Aushalom of the University of California at Santa Barbara, who heads one of the world's leading Spintronics labs. Thanks for speaking to me today, David.
It's my pleasure.
What exactly is Spintronics?
Spintronics is a new area of technology that's based on trying to manipulate the spin of a particle in contrast to its charge. So today, most of our technology is based on taking electrons and moving them on and off the devices of circuits, transistors, diodes, resistors. But so far, no one's exploited the fact that every electron also has a spin. Much like the Earth precessing on its axis. It can spin left or right, but also the fact that spin is a quantum variable in nature, which means it can exist in this unusual superposition of up and down. And people are trying to come up with ways to understand how you might control that in different types of matter.
How is Spintronics currently being used in electronic devices?
Right now, you can actually buy Spintronic devices as ways to read out your hard drive in laptop computers, PCs in general. It's a way to very efficiently read very small pieces of magnetic information that are stored on your drive. And one of the beauties of a Spintronic read head, which is made of different types of magnets stacked on top of one another, is it's extremely sensitive to small magnetic fields. So the resistance of a current that passes through this head is very sensitive to the presence or absence of a magnetic particle nearby. And it becomes a very efficient way to quickly read out information reliably. So it exists, and you can buy it in a hard drive, but it's based on metallic systems.
Why is Spintronics an important technology for the future?
Well, that's a good question. It's an important technology because it's one of the few technologies that is really based on an opportunity to exploit quantum physics, a quantum variable. So right now, when we store information, we store it in two states, up or down, with binary logic, 0 or 1. The information is there or not there. But somehow building a technology based on a quantum variable means that you can store information in a superposition of these states. So in a simple example, it's a way possibly to radically increase information storage from what we have today. So when you think about every bit in some storage device, flash memory, or your hard drive, it's either there or not there. It's a 1 or a 0. So a physical piece of matter stores two pieces of information, 1 or 0. A spin of a particle, which you could think about it like a needle that can point in any direction in 3 dimensions, and whose tip would trace out the surface of a sphere. Every point on that sphere is a data point. So one electron, in principle, can store an almost infinite amount of information. So when you think about scaling it, it could have a mercurial change in storage technologies. That's one reason. The second is, which I think many people have heard about, is building quantum machines or quantum information processors, which require entangling quantum states of matter. And spin is a quantum state. And so it's one pathway to building quantum systems.
What are the main challenges that must be overcome to create commercially viable Spintronics devices?
Well, I think there are plenty of challenges. There are challenges in both trying to understand how you can efficiently manipulate quantum mechanical states in real materials. So there's a lot of work going on right now to think about how you might engineer materials to make that job a little easier. Changing the band gaps of semiconductors, changing the effective masses of particles. There's also the issue about thinking about architectures. How could you build a quantum machine that would be inexpensive and reliable? Today we think about building classical machines with millions of bits. Well, maybe in a quantum machine, 10 or 100 quantum bits would be plenty. And how would you configure 10 or 20 or 100 quantum bits to do something unique? So there are challenges from the computer science direction, from the material science direction, and from the fundamental physics direction. So I think for students from different disciplines, this is a very exciting time to be in these areas.
And finally, how is your research furthering our understanding of Spintronics?
Our research focuses largely on semiconductor spintronics. And semiconductor spintronics is focusing largely on how you can get a handle on these quantum states in real matter. So it means, can you use, for example, the electric field to manipulate the spin of a particle? And traditionally, we think about using the magnetic field to manipulate the spin of a particle. But in building a technology, much like you asked earlier, you need to be able to locally play with spins of particles on the atomic scale. And it's a little easier to do that electrically than magnetically. So we work quite a bit on trying to understand how quantum states interact with real matter, how quantum information gets lost moving through real matter, and how you can manipulate it very quickly before the information is lost to the matter. So my own group works largely on the fundamental aspects of manipulating quantum information. We're quite far away from building anything practical.
Okay, well, thank you for speaking to me today, Professor Ashland.
Thank you very much for having me.